These massive flared panels bulging off the rear of every new freight locomotive were not there 20 years ago. Older diesels handled 4,000 horsepower with shrouds barely 90 inches wide. Today's units stretch past 106, yet they do not make more power. So why are locomotive radiators suddenly so enormous? Most people assume bigger engines and hotter running. The real cause is a clean air regulation that quietly forced engineers to reject an extra half megawatt of heat they never had to deal with before. And the two companies that build nearly every North American locomotive chose very different ways to cope. Through most of the late 20th century, the cooling systems on North American freight locomotives followed a simple pattern: compact, rectangular radiators tucked neatly into the rear of the long hood. The EMD SD42, a mainstay of the 1980s, ran 3,000 horsepower through a 4-section radiator core, each side segment just 27.5 inches long. The total effective cooling area landed around 16 to 18 square feet, with 4 modest fans moving air over the fins. Even the GE-9, a high-horsepower workhorse from the 1990s, stuck to a single wide shroud, about 90 inches across, housing a pair of large fans and roughly 10 square feet of open frontal area. Service manuals and engineering drawings from that era show a focus on modularity and repairability. The SD42's side sections could be unbolted in the field, while the -9's deep wing fins squeezed more cooling from a fixed width rather than by expanding outward. Despite the horsepower arms race, 3,000, then 4,000, then 4,400, the outer shape of the radiator barely changed. The basic envelope stayed close to 90 inches wide, with the fin area rarely exceeding 12 square feet. These designs handled the waste heat of massive V16 diesels without the need for bulging panels or oversized shrouds. Even as engines grew stronger, cooling capacity kept pace through denser fins, higher airflow, and incremental tweaks, not radical expansion. This compact form became the visual baseline for decades. Locomotives from the 1980s and the 1990s lined up in yards with straight-backed radiator housings, none of them stretching far past the car body. The contradiction now stands out. If older engines ran just as hard, why do today's locomotives need such enormous radiator wings? The answer is not found in the horsepower ratings, but in a new set of rules that rewrote what it means to keep a diesel engine cool enough. Every freight locomotive runs on a simple thermal principle. The engine burns fuel, and most of that energy turns straight into heat. For a 4,000 horsepower prime mover, nearly 2 megawatts, about enough to power 1,500 homes, has to be dumped somewhere. Every minute the train is working hard. The only thing standing between the engine and a meltdown is the cooling system, and at the heart of that system is the radiator. The cooling loop starts with a heavy-duty pump, pushing a mix of water and antifreeze through channels in the engine block. This coolant absorbs heat from the cylinders and heads, then races toward the radiator, a dense wall of metal tubes lined with hundreds of thin fins. As the coolant flows through, big fans spin overhead, pulling outside air across the fins. The heat jumps from the hot coolant into the metal, then into the air, and finally out the back of the locomotive. The goal is to keep the coolant below 95 degrees Celsius, or about 203 degrees Fahrenheit, because anything hotter risks engine damage and, under modern rules, emissions violations. The physics is simple, but relentless. The heat rejected, Q, equals the heat transfer coefficient, U, times the radiator area, A, times the temperature difference between coolant and outside air. The pump can only push so much water, and the temperature cannot go past the EPA's ceiling. That leaves only one real lever for engineers: surface area. When waste heat goes up, the radiator has to get bigger. There is no shortcut. Modern radiators pack in more fins per inch and use stronger fans, but the basic anatomy has not changed in decades. What has changed is how much heat they are asked to handle. The moment emissions controls, like cooled exhaust gas recirculation, enter the picture, the cooling loop faces a new flood of thermal energy. Suddenly, expanding the radiator is not just a matter of comfort or efficiency, it is the only way to keep the engine legal and alive. That is why, when regulations force more heat into the system, the radiator has to grow, no matter how awkward or expensive that might be. North American freight locomotives are shaped by a contest between two giants, GE, now part of Wabtec, and EMD, owned by Progress Rail. These two companies delivered nearly every new mainline locomotive in the US and Canada from 2015 to 2022. GE and Wabtec accounted for about 55% of those deliveries, while EMD and Progress Rail supplied around 35%. The remaining sliver, less than 10%, went to specialty builders and importers, a rounding error in the world of heavy freight. Both GE and EMD faced the same regulatory wall, the EPA's Tier 4 emissions standard, which took effect in 2015 and demanded a dramatic cut in nitrogen oxides and particulates. Meeting those limits was not optional. The question was how to do it without crippling the locomotive's performance, or making it too heavy, too costly, or too complicated to run. Each company had its own engineering traditions and business pressures. GE, with its Evolution series, had built a reputation for fuel efficiency and modular design. EMD, now under Caterpillar's Progress Rail, leaned on decades of reliability and a vast installed base of its 710 engine. The stakes were enormous. Whoever solved the Tier 4 puzzle most effectively would dominate the market for years, locking in orders from the biggest railroads and shaping the look of every new freight train across the continent. Yet the regulatory demand for cleaner exhaust forced both companies into unfamiliar territory. The old tricks, tweaking combustion, squeezing out a few more points of efficiency, no longer worked. The only way forward was to pick a new emissions control strategy, knowing that every choice would ripple through the entire locomotive, from the fuel system to the cooling fans. The result was two different approaches, each with its own set of compromises, and both leading to the same visual outcome: radiators that dwarf anything seen on the locomotives of the past. The near duopoly meant that decisions made in a handful of boardrooms and engineering labs would set the standard for the entire continent. The path each company chose, whether to chase after treatment with chemicals or to wrestle the heat burden of cooled exhaust gas recirculation, would not just affect emissions numbers on a spreadsheet. It would dictate the size, weight, and shape of the machines hauling freight from coast to coast, and ultimately, what kind of trade-offs railroads would have to accept to keep moving goods under the new rules. On January 1, 2015, the EPA Tier 4 rule set a new bar for freight locomotives in North America. Nitrogen oxide emissions were capped at 1.3 grams per brake horsepower hour, an 80% reduction from the previous standard. Particulate matter limits dropped to 0.03 grams per brake horsepower hour. These numbers left little room for compromise. Every new or rebuilt locomotive had to meet these targets, not just at the factory, but throughout its entire working life. The law's language was clear: keep engine coolant below 95 degrees Celsius, or face penalties. This single requirement forced manufacturers to rethink engine design from the inside out. Lowering combustion temperatures to cut nitrogen oxides was not a matter of tweaking settings. It meant reimagining how engines handled air, fuel, and heat, all while maintaining power and reliability. For GE and EMD, the two giants of locomotive manufacturing, Tier 4 was a turning point. Meeting the new nitrogen oxides and particulate limits required more than incremental changes. Engineers faced a cascade of choices: including cooled exhaust gas recirculation, selective catalytic reduction, or a complete overhaul of engine architecture. Each option brought trade-offs, including added hardware, extra weight, more complexity, or the need for much larger radiators. The pressure was immediate. Failing to comply meant losing access to the largest freight market in the world. Success brought its own challenges, as managing the extra heat became a daily reality for operators and maintenance crews. In this new era, emissions law shaped every locomotive's design, pushing the industry to adapt or fall behind. Exhaust gas recirculation, known as EGR, starts with a simple but powerful idea. Take some of the hot exhaust leaving the engine, cool it down, and feed it back into the intake. This is not about recycling energy or squeezing out more power. The real purpose is to change the chemistry of combustion itself. When exhaust gases mix with fresh air, they dilute the oxygen in the cylinder. That dilution lowers the peak temperature inside the combustion chamber by a significant margin, often hundreds of degrees Celsius. This temperature drop is the key, because nitrogen oxides, called NOx, form most aggressively at high heat. By keeping the flame cooler, EGR can suppress NOx generation by around 40% compared to untreated combustion. But the process only works if the recirculated exhaust is cooled first. Raw exhaust can hit 650 degrees Celsius as it leaves the cylinders, far too hot to send straight back in. An EGR cooler brings that temperature down to roughly 120 degrees Celsius, using the same coolant loop that already protects the engine. The result is a safer, more controlled burn, with much less NOx leaving the stack. This thermodynamic trick is elegant, but it comes with a hidden cost. All the heat pulled out of the exhaust by the EGR cooler does not just vanish, it gets dumped into the locomotive's main cooling system. For a modern 4,400 horsepower engine, that means an extra 25% heat load on top of what the radiator already handles. The emissions win is clear, but the thermal burden is massive. Suddenly, the radiator is not just fighting the heat from combustion, it is also absorbing the extra energy needed to keep EGR effective and the engine legal. That is the trade-off at the heart of Tier 4, cleaner air, but only if you can find a way to shed all that new heat. A Tier 4 locomotive working at full throttle faces a thermal reality that is easy to overlook. Cooled exhaust gas recirculation dumps half a megawatt of extra heat into the cooling system, on top of the 2 megawatts already flowing from the engine. The Environmental Protection Agency's hard line on nitrogen oxides and particulate emissions forced manufacturers to keep coolant temperatures below 95 degrees Celsius, no exceptions. That target is non-negotiable, because anything higher risks not just engine damage, but an emissions violation. The numbers drive the hardware. When exhaust gas recirculation coolers drop exhaust gas from 650 to about 120 degrees Celsius, every kilogram of recirculated exhaust soaks up energy that the radiator must reject. For a 4,400 horsepower prime mover, the added heat load from exhaust gas recirculation alone can reach half a megawatt, about a 25% jump over legacy engines. With pump capacity and airflow already near their limits, the only lever left is surface area. That is why the radiator wings on Tier 4 units are not a stylistic flourish. They are a direct response to physics. The payoff is visible in the numbers. GE's Evolution Series locomotives, for example, grew their radiator shrouds by about 16 inches in width, nearly doubling the frontal area compared to their predecessors. The total finned surface increased by roughly 50%, enough to keep coolant below the regulatory ceiling even on the hottest days. This expansion is not free. It adds weight, increases aerodynamic drag, and complicates maintenance. Yet compared to the alternative, an 8,000-pound SCR system, urea logistics, and higher upfront costs, the big radiator remains the lesser evil. In the end, emissions law, not horsepower, now dictates the shape and scale of every new locomotive cooling package. The next design reset may come with batteries, hybrid drives, or hydrogen stacks, each rewriting the rules for how trains manage heat. As the EPA's Tier 4 deadline approached, North America's two locomotive giants faced a defining choice. GE, soon to merge with Wabtec, committed early to cooled exhaust gas recirculation, EGR, after weighing every alternative. Their engineers saw selective catalytic reduction, or SCR, as a path burdened by extra weight, a urea tank, and a new supply chain for diesel exhaust fluid. EGR posed its own challenge: how to manage a surge of heat without damaging the engine. GE decided bigger radiators were the lesser headache. By 2012, they locked in the EGR-based Evolution series, betting that cooling upgrades would be simpler than chemical aftertreatment. Tier 4 units rolled out in 2015. Their oversized radiator wings were a direct result of this call. EMD, under Progress Rail, started with SCR, adapting their trusted 710 engine to meet emissions rules using urea injection and a diesel particulate filter. The SCR kit alone weighed nearly 8,000 pounds and strained the underframe. Cooling systems lagged and catalysts wore out quickly. EMD pivoted. By 2015, they launched the SD70AC T4, built around a new 1010 engine with moderate EGR and a radiator nearly as large as GE's. Both companies ended up with locomotives shaped by cooling needs more than horsepower. The new rules did not just clean the air, they changed the look of every freight locomotive on the rails. The oversized radiator isn't just an engineering headache, it's a daily reality for the people who keep freight moving. Each extra panel and fan adds weight, drag, and complexity that ripples through railroad operations. A Tier 4 radiator assembly weighs about 1,200 pounds more than its predecessor. That's enough to shift the locomotive's center of gravity and bump up the total weight by nearly 3%. For maintenance crews, the old one-person lift is gone. Now replacing a radiator means a two-person job and special handling gear. Swapping out a Tier 4 radiator can tie up a shop for 16 to 32 hours, double the time of older units. The parts bill alone often tops $30,000. The aerodynamic penalty is real too. The winged shroud increases drag by about 1%, which translates to a measurable hit on fuel economy, roughly a 1% increase in fuel use, just to push the bigger shape through the air. That may sound small, but across a fleet, it adds up fast. Railroads have to weigh these costs against the alternative: an 8,000-pound SCR system, urea tanks, and a whole new supply chain. In the end, the big radiator is the trade-off most operators accept because it's simpler to service and avoids chemical logistics. For shop crews and fleet managers, the paradox is clear: comply with emissions law or face an even bigger operational burden. The shape of today's locomotive is dictated as much by environmental rules as by horsepower, and every extra pound and hour in the shop is the price of cleaner air. The oversized radiator wings on North American freight locomotives are a direct answer to a regulatory and engineering paradox. When Tier 4 rules forced manufacturers to slash nitrogen oxides and particulates, they faced a choice: use cooled exhaust gas recirculation and deal with a massive new heat burden, or adopt selective catalytic reduction, SCR, and take on even more weight, cost, and complexity. The numbers tipped the scales. An SCR system for a freight locomotive adds about 8,000 pounds of hardware, including a urea tank and dosing equipment. This is not just dead weight, it eats up valuable underframe space and requires a whole new supply chain for diesel exhaust fluid. For railroads running across vast remote regions, that logistical headache was a deal breaker. GE and EMD both ran the math. Expanding the radiator shroud Adding those now iconic wings meant a penalty of about 1,200 pounds and a modest hit to fuel economy. But it kept the locomotive fuel agnostic, easier to service, and free from the risks of urea shortages or catalyst failures. The paradox is that the ungainly radiator wings are actually the more efficient compromise, not a design failure. Europe, under Stage 5 standards, faced the same emissions challenge but with a twist. Locomotives there are boxed in by a strict 2.9-meter width limit. Instead of flaring out, European builders tuck SCR modules and urea tanks under the frame, using compact, high-efficiency aftertreatment. The result is a slimmer profile, but a heavier and more complex machine. Different continents, same emissions goals, radically different packaging. The shape of the locomotive now follows emissions law, not horsepower. The next design reset may come from batteries, hybrids, or hydrogen, each with its own cooling puzzle to solve. Today, the size of a locomotive's radiator isn't driven by horsepower, but by the unseen heat burden of emissions control. Cooled exhaust gas recirculation became the least bad compromise. Its massive radiators are a physical signature of clean air law shaping steel. GE and EMD chose different engineering paths, but both bowed to regulation. As battery, hybrid, and hydrogen technology emerge, the next reset may change the silhouette all over again. What would you choose, size, complexity, or the air we breathe?